Chapter 3 has to do with project management. You are familiar with projects whether you realize it or not, because taking a course at a university level is a project. And we will talk about what makes a university course a project. In this chapter, we have some objectives. We're going to do a network diagram. AON stands for activity on node diagram. There's various types of drawings, but we will focus on the activity on node drawing or diagram, which we'll also use in our software. We are going to do what is called the forward and the backward pass for calculating the start and end times of various activities. We will also determine the critical path, and we will also crash a project. Now, what makes something a project? It has specific goals. When you look at a course, that would be identified in the course outline. What are we trying to achieve? Why are we taking a chapter on project management? Because it's in the course outline. Projects are unique, and so they are even so they're different than regular operations. So even if you build a house that's quote the same as the one next to it, it's not, because it's on a different piece of land, and there may be different laborers working on it, and there may be different colored carpet, and so it is unique, even though you have familiarity with it. They're team-based, because these days projects can be quite complex, like designing a new iPhone, for example, or even designing software for teaching courses online. It's not done by one person or one type of skill set. They are temporary, just like this course is. It has a start and it has an end to it. When you complete the final exam, they're marked and your marks are submitted, then the course is completed. And it goes again across organizational lines with regards to, it's very interdisciplinary. So you'll have an accounting person, perhaps a marketing person, an engineer, operations management person. Now, the WBS is a critical component of understanding what project management is all about. So you start off at a very high level, just describing the project. So in this particular case, operations management would be the project. Then you have the major tasks, and these are also called deliverables. So what students quite often look at, what do I have to do to pass this course? How many assignments are there? Is there a midterm? Is there a final? And you break it down. Is there a report? In our particular case, there are assignments, there are quizzes, there's a final exam, and depending on which version of this course you take, there can be a midterm or not. And there are the simulations. Then you have the subtasks, putting things together, and then the work packages. And the work package is simply the smallest element. It can't be broken down any further. So we'll just deal with 4 levels. You can actually get more levels, but that is sufficient for our needs. So here's an example of the type of development. This is for Windows 8, a couple versions ago. And you would see that that was the overall project, develop an operating system. And you can see that there was, on the far right-hand side, there was system testing, there was module testing, and then defect tracking, which is part of fixing things fixing the bugs before it goes out to the customer or consumer. Now, you need to identify the project sequence. And in this case, you need to also identify the relationships. So one of the things you'll do is, if you are a student who's taking, say, an irregular set of courses, and not in the standardized way, you'll probably talk to an academic advisor to make sure, I'd like to take this course, and you need to find out what the prerequisites are. So for a lot of you, there are prerequisites for courses, and you have to be careful that you don't wind up being at the end. You've got, say, 2 courses left, but one's a prerequisite for another. You would like them to not be in the prerequisites, so you can take them at the same time. You'll also identify the time and the cost, and obviously identify any materials you need, worker requirements, not only the number of workers that you need, but the type of worker. Do I need a carpenter? Do I need an electrician? And within the specialty areas, a roofer at some point. And we need to identify the critical activities which will be on the critical path. So the purpose of the scheduling, I'm not going to go into this in huge detail, but just to show the relationship, like the order that things go in, which is point number 2, the precedence relationships. And it also is to try and determine what is a reasonable or realistic time and budget or cost. And we're trying to make more effective use of our resources. So in this particular case, how you would read this is you can start immediately 2 activities. A, you can build the internal components, and B, you can modify the roof and the floor. So there are no immediate predecessors. So you can start those at time 0. Activity C, which is constructing the collection stack, cannot be done until activity A is completely done. So you can't start C at time 0. C has to wait for A to be completed. D, pouring the concrete and installing the frame, not only has to wait for A to be completed, but it also needs to have B done. So you need both of them. It's an and situation. And you can see the rest. E cannot start until C is completely done. F, same thing. G has to wait till D and E are done. And H, the inspecting and the testing, has to wait until F and G are done. So here's an activity on node diagram. The node, by the way, is simply the circle. And you can see that activity A and activity B are parallel activities. They can be occurring at the same time. They're not sequential. Sequential would mean that you have to do one after the other. So here's again, this is just drawing out the network diagram from what we had in the listing on that table. And here we are with the completed diagram. So what you see is when A is done, then C and D can start. But D also has to wait for B to be completed. And you read the diagram from left to right. And you can see the little arrowheads. And so you read the diagram from left to right. And it doesn't matter vertically, like this, the A and the B could be reversed. And of course, our diagram could be flipped. Then, D would go up. All right. So the critical path, as you can tell by the name, it's the most important path. It is the longest path. It's not the shortest path. It's the longest path through a network. So if you had 2 paths and one is 17 days and one is 23 days, the one that's 23 days will tell you how long your project's going to take. And even though it's the longest path, because all activities need to be done, it's the shortest time which the project can be completed. A very important factor with critical path is the fact that any delays on the critical path delay the entire project. And it has 0 slack, which we'll talk about in a moment or two. So here's again the tasks, but in this particular case, you have times with it. In the previous one, we didn't. So you plug in the times and you calculate 4 things. Doing the forward pass, you calculate earliest start and earliest finish. And as you can see, the earliest start is the earliest you can start something, just by what the name says. And what's the earliest I can complete or finish something is the earliest finish. The latest start and latest finish are done during the backwards pass. And so a latest start is what is the latest I can start something without delaying the entire project. And the same thing for the latest finish. What's the last possible time I can complete it, the activity that is, without having the whole project be late. So you can see you have this bubble or this circle, and this is very common for a notation. Top left is earliest start, top right is earliest finish. and then you have latest start and latest finish on the bottom. You have the activity, and the activity has to be unique. You cannot have two A's or two B's. You have only one A. So in this particular case, when you are moving forward, and you have two paths that converge, you take the longest time. That's what this all means at the very bottom. If you have two different completion times, you take the larger number when you're moving forward. You take the earliest finish is simply the starting time, which is the earliest start, and add the duration of the activity time. And this hopefully will become more clear in a moment when we actually do some of the calculations. Now, when you're moving backwards, when you're moving from right to left, which is the backwards pass, and you have multiple numbers to choose from, you pick the minimum number, and I'll show you that in a moment. The latest start is the opposite. So on the top of the diagram, you take the earliest start and add the activity. When you do the backward pass, which is from right to left, as I mentioned, you take the latest finish and subtract. So on the top you add, take the maximum number, and on the bottom you subtract and take the minimum number when there are multiple numbers to choose from. So in this particular case, what you see here is, by the way, the start node is simply a dummy activity. You have to have one starting point and one ending point, and the dummy activity has no resources. You can see it has a time of 0. So activity A starts at time 0. It takes 2 time units to complete, in this case, and so 0 plus 2 is 2. Then you take the 2 and you move it forward to C, and there's only one path, there's only one way to get to C, and that comes from A. So the 2 in the top right-hand corner of A becomes the 2 in the top left-hand corner of C. Activity C also takes 2 time units, and that becomes 2 plus 2 is 4, and you move forward. So to continue on with C, the 4 in the top right-hand corner becomes the top left-hand corner, which is the earliest start for F, and it's also the earliest start for E. There's only one way to get to F. There's only one line that gets from into F from the left, and that's from C. Same thing with E. So that F takes 3 time units, so 4 plus 3 is 7. E is 4 time units, so 4 plus 4 is 8. Now you have another path that comes along on the bottom here. And I won't do all the math for you, but when you come to G, you actually have 2 possibilities. You have 8, which is the earliest finish from E, and you have 7, which is the earliest finish from D. And so you take the larger of the 2 numbers. So in G, for the top left-hand corner, you have 2 possibilities, a 7 or 8. But as I mentioned before, when you move forward, you take the largest number. Then 8 and 5 is 13. Now the same thing happens for H. When you calculate H, you have 2 possibilities. You have the 13 from G in the top right-hand corner, and you have the 7 from F, which is in the top right-hand corner. When you move forward, you pick the largest number. So we'll pick the 13. And then you add 2, and you get 15. Then you do the opposite when you move backwards. So in this particular case, what you need to do is this. The 13 in the bottom left-hand corner of H becomes the 13 in the bottom right-hand corner for F. You take the 13 minus 3, you get 10. And you do the same thing for all the other diagrams, or all the other nodes, sorry. Now the slack is the difference between the top numbers and the bottom numbers on either the left or the right-hand side. So it's either latest start minus earliest start, or latest finish minus earliest finish. You'll get the same calculation either way. So in this particular case, what you do is, for activity A, if you take 0 minus 0, you get 0. Or if you take 2 minus 2, you get 0. So either way, when you have a slack of 0, it means the item is on the critical path. So just looking down at the slack, A is on the critical path, C is on the critical path, E, G, and H are all on the critical path. And so any delays to either A, C, E, G, and H will cause your entire project to be late. If B is delayed by 1 time unit, that just uses up the slack. So if B is delayed by 1 time unit, now your slack is 0, and now it becomes part of the critical path. Same thing with D, but F has 6 time units of slack. So for example, if somebody were to take 2 days off for A, your project's late by 2 days. If somebody takes 2 days off for B, your project's only late 1 extra day because you have 1 day of slack. And if somebody is off for F, all it means is your project's still on time, but now the 6 days has become 4 days of slack. So identifying where the slack is very important for determining the critical path. And you must have at least one critical path. It is possible to have more than one critical path, but you have to have at least one. One other point, you can see that on B and D, there's 1 day of slack. That's in total. You can't delay B by 1 time unit and D by 1 time unit. It's or. So there's only 1 day of slack between B or D. All right. And so you can see the critical path is now, as they do it here, in the thick blue lines. And in Microsoft Project, they do it in red, although you can change that. So one of the things about being a project manager is trade-offs. You people experience this when you are looking to get say a term paper completed or even an exam. You have a limited amount of time and you want to know where to spend your time. So maybe you spend a little less time on your report on the budgeting section because you need to spend more time on the SWOT analysis or things along this line. So it's all about trade-offs between the 3 binds. The 3 binds are time, cost, and scope. So how long it's going to take, how much it's going to cost you, and what are you trying to achieve? So when we come to project crashing, means your project has fallen behind schedule. So you need to find ways by adding additional resources at an additional cost to get your project done sooner. The crash slope, or in this case they call it crash cost per period, which is crash slope. You take the crash cost, subtract the normal cost as the numerator. The denominator is normal time minus crash time. One of the things with this, you'll get a negative number. You will always get a negative number. And in project management, it's known that the number is negative, like it's always, but they just drop the minus sign because otherwise every single answer would have a minus sign in front of it. So they just say the slope is 3, but it's really negative 3. So you have to crash the critical path. And if you shorten a path that's not critical, this is what happens. Your project still takes the same length of time and you spend more money, which is lose-lose. So you crash items that are on the critical path. And you can see the steps in the process, which we'll go through with some examples later on. Now, in this particular case, you can see that we have A is on the critical path, C is on the critical path, E is on the critical path, G and H. The cost in this case per week is $750 to shorten A by 1 week. To shorten C by 1 week is going to cost you $1,000. E $1,000, G $1,500, and H $3,000. They will all have the same effect on time. It says per week. I would rather spend $750 to shorten my project by a week, as opposed to the worst is H, which is $3,000. Now, why don't I crash F because it's only $500 because F is not on the critical path. So what would you do? You'd spend $500 and your project would still be done on or in the same length of time. So you would spend more money and have no effect on time. So you have to pick a critical path item. You also notice that for A, you can go from 2 days of normal time to 1. So you can only crash it 1 day, what I refer to as crashability or ability to crash it. You can see that in this case, B, you can go from 3 to 1. So you can actually crash it twice, but B's not on the critical path. G, you can go from 5 to 2, so you can crash it 3 days, but it's $1,500, so it's rather expensive compared to some of the other critical path items. So you go from the least costly to the most costly, but it still has to be on the critical path. And you can see the slope, as I mentioned before, it is negative. It's always downward sloping. So in this particular case, you can see the differences. You've got 34,000 to complete the activity in 1 week, 30,000 to complete the activity in 3, because you might need to hire some extra laborers or pay them overtime or some extra equipment, whatever this particular activity is. So another $4,000 to reduce it by 2 weeks. Well, that works out to be $2,000 a week. And like I said, if you pay attention to the math, the number is actually negative. Although they've switched the formula around to be a positive, but in project management textbooks, it's always a negative. So either way, it costs you $2,000 to crash it by 1 week. It costs you $4,000 to crash it by a second week or in total. And in this case, you can only crash it from 3 to 1. So here's the same diagram as before, but we have crashed the project. So now we'll move on to some examples, and I hope you've enjoyed the presentation on Chapter 3.